Hi everyone, welcome back. I just wanted to clarify something about these problems. There's this word excess that gets thrown around a lot, and I just want you to know, because sometimes the answer is not clear. Do they want me to go to the hydrate, or do they want me to go back to the carbonyl? These kinds of questions do come up. Do they want the acetal or do they want the hemiacetal? So for example, I think you can see when we say excess, we want you to use multiple equivalents oftentimes. So you know you're going to get the acetal. But when you have the acetal and you're going back to the hydrate, sometimes there's a little bit of a question. Later you'll see that often we don't want the hydrate. We want the carbonyl group regenerated. And so here I drew a little scheme of how that happens. In acidic conditions, you will get protonation here, which converts that to a good leaving group, and then this oxygen's lone pairs come down and kick that out. So that's how we regenerate the carbonyl. And in an equilibrium between a carbonyl and a hydrate, the carbonyl is usually favored. So I have that written in the answer key. When you favor the carbonyl, it's because of the acidic conditions. But let's say that I added water to this, then that's going to drive the reaction toward the hydrate. So I know the answer is the hydrate in this case because it says excess water. But if it just said H plus H2O, I would expect it was just a little bit of H plus, and that little bit of H plus could favor the carbonyl group forming. Later, in a couple of sections, you'll see that when you have the hydrate and you see H plus H2O, they actually want you to go ahead and convert it to the carbonyl group because that's thermodynamically more stable. So just FYI, in this case, we have the hydrate because it says excess water. If it didn't say excess water, it just said H plus H2O, then we'd probably take this and convert it all the way to the ketone or aldehyde. So keep that in mind because we're going to use that later. All right, let's start with this section here. A couple reactions that are a little bizarre that don't really fit the general form that we've been using, which all these reactions are basically the same mechanism. It's either nucleophilic attack and addition, or it's nucleophilic addition followed by an elimination or a leaving group of some kind. Okay, so here's an example of an addition, and then here's an example of an addition and an elimination. All right, so a couple of reactions here that are a little bit miscellaneous, but we use them also, and they're good to know. Okay. This one here is called the Wolff-Kishner reduction. And what this does is it changes a C double bond O's to a CH2. It just completely gets rid of the oxygen. All right, so it's a pretty amazing thing, and you might wonder, well, how does that happen? And do I need to know that on the exam? Well, you should be able to do part of it. You should be able to do this first part because basically it's the imine formation, and we covered that. So what you're doing is you're taking this molecule called hydrazine, N2H4, and one of these nitrogens is going to attack here, and then you're going to have the two N's as part of this imine. Okay, you should be able to figure out the mechanism for this, so go ahead and I'll leave it up to you to try that and check your answer in the answer key. What I really want to focus on now is your understanding of mechanism. Can you look at a chain of events and sort of figure out what's going on with electron pushing arrows? Okay, so this will help you sort of develop your sense of how the electrons flow. If I look at this going to this, I notice two H's and only one H, and I know this is a strong base. So for this step, I would expect you to be able to take one of these H's and plop that lone pair onto this N. And so that's how we do this step right here. There are 4 steps that get us to here, and this is the 5th step. Okay? Now at this point, I want you to figure out, how do I go from here to here, and how do I go from here to here? 2 products, nitrogen gas and this carbon ion, and it really helps to draw in the lone pairs. And then from here, ultimately, to here. And remember, our overall goal was to change this carbonyl group into a CH2 group. That's reduction. Okay, so I'd like you to take a moment and see if you can figure out how the electron pushing arrows flow with these 2 reagents to make this intermediate, and then with this reagent to make these intermediates, and then finally to the end product. So fill in the arrows for me, and then we'll come back and check our answers. All right, guys, so in this second step, I see that I'm trying to make a pi bond here, and I have electron-rich center here, so I'm going to use those to push the electrons. So I'm going to push the electrons this way, and then I have to figure out what to do to get this H on here. So probably what I'm doing is, instead of flowing these electrons to carbon, I could do that, make this a temporary anion, and then pick up the H2O. Or I could maybe combine those two steps and pick up the H2O. Go ahead and do that. And we're in a basic condition. You may say, well, water's, OH minus is not a good leaving group, but we're in basic conditions, OH minus floating around everywhere. All right. And they're, constantly exchanging, hydrogens with each other, so water turns into hydroxide, hydroxide turns into water, back and forth all day long. Okay. So, that's how we get this H is from water here. Now in this next step, notice that this double bond, this pi bond that we generated here is part of this nitrogen. Nitrogen is very stable, so the driving force is the thermodynamics here. So what I want to do is I need to flow electrons this way because I have a negative charge on the carbon. So I think I'm going to take this lone pair on the nitrogen and make my triple bond here and break this bond so that my nitrogen is freed up. But I also have this hydrogen here that's not here. So I need to get rid of this hydrogen. So maybe I'll back up a little bit and I'll say, what if I use this OH to grab the H, and then the bonding electrons can move down here, and then that lone pair is still there. And then I can just flow the electrons to the carbon and get this lone pair right there. Okay. In the next step then, I just need to protonate that, so I end up with 2 hydrogens on this carbon. So I just borrow one from water right there, and I generate OH minus. So that's the Wolff-Kishner reduction. Okay, so these are the steps that fall in line with addition-elimination reaction that we learned. So I would like you to be able to apply it here without any help. But this next part is a bit tricky. I don't expect you to memorize this part. Probably most, likely I would just step you through it like I have here and ask you to provide the electron pushing arrows, or I provide the arrows, you provide me the intermediates, or some combination of that where I give you a little guidance, okay? But I do want you to understand how that works, and I want you to know the overall reaction is, so that you can use it in your synthesis. I want you to know when you have a carbonyl, the reagents you need are, one, you need this hydrazine, and you can write it as in this format or in this format. You see it both ways often. Step 2, you need the hydroxide. See, we have hydroxide here and here. It's in water. Sometimes you see water, sometimes you just see hydroxide aqueous or just hydroxide, but they mean aqueous. And oftentimes you see heat as well. All right, so what that's going to do is that's going to give you the reduction. So notice carbonyl gets reduced to a methylene group, CH2. All right, so please write that down, remember it, work out the mechanism for the first part. That's what I'm asking you to do right now. This next reaction is called the Wittig reaction, and it's really amazing, okay? This is how the mechanism of it works. Again, it's a little bit complicated, doesn't follow the pattern that we've been learning. So I will have to step you through it if I want you to know some of it. I want you to mainly to just get the ideas behind how it works, but I don't expect you to memorize it and write it out from scratch, okay? For this, we're using a strange reagent. You've probably never seen this before, triphenylphosphine. Phenyl groups can be abbreviated pH, so that's 3 pH groups. And then we've got this alkyl halide here. This is a nucleophile here, so this can attack here like an SN2 reaction. And then once we have that, then we have phosphorus with 3 phenyl groups attached to this carbon. And this carbon's got this R prime group on it, and it has the 2 hydrogens still. I'm going to write the 2 hydrogens separately, actually. All right. Now the next step is we use a strong base like butyllithium Okay, so this is sort of like Grignard reagent. It puts the negative charge on the R group. In fact, many times I like to just polarize this bond completely and just think of it as ionic. It's not accurate, but it's good enough. It helps me to figure out what's going on. So this will come in, and as a strong base, it will have the ability of deprotonating this carbon. At that point, we make a very important intermediate called an ylid. Okay, so id. Okay, that's how it's pronounced anyway that I've heard it. And so this ylid has a lone pair on the carbon. Now, a resonance structure of the ylid is sometimes also shown in problems, so it's helpful to understand that. Sometimes you see something like this. Now, phosphorus already has 3 bonds. You might wonder, how does it have 5 bonds? It's in group 3, like with chlorine and sulfur. They can expand their octet. So this is how it becomes neutral. It's in group 5 and it has 5 bonds, so it's neutral. Okay. Once we have that, then it can react with this. And here's how it does that. Okay. You can either think of the ionic form of it or the double bonded form of it. I'm going to use the ionic one, or actually, it doesn't really matter. Let me maybe just use this one here. I'm going to draw this. Ketone looks sideways. Sorry about that. Okay. So basically, the O and the P can make a strong bond. Maybe you're familiar with phosphate groups, right? So PO is going to be a good bond to form. So I'm going to, basically the idea is my carbon of the carbonyl is usually the electrophile. You've learned before that alkenes are nucleophilic. So I'm going to attack this way, and then I'm going to attack that way. And so you end up with these being attached to each other. So notice I made a carbon-carbon bond right here between the ketone and the carbon of the ylid. Here's my ylid. And then my phosphorus, oh yeah, it hasn't made a bond yet. So actually the O, I've shown it all happening at the same time in a 4-membered cyclic transition state. You can also show it stepwise to get there as well. So they broke it down a little bit here. Again, this is from the Sturmanis textbook. So if you just use the ylid, you can just do this, and that's how you get here. Then if you go from here to here, notice you make a new bond right here. So all you have to do there is attack right here, the phosphorus. Now if you want to combine these 2 steps and just get to here directly, you can do what I did down here. Just do it simultaneously. At that point, remember I said this is a favorable bond to form. We can collapse this cyclic transition state down by, something like that. Okay, ultimately, what are we doing here? We've got this kind of a group here that eventually turns into an ylid. And we've got a carbonyl group, and these 2 make these 2 products. Now, oftentimes we don't write the phosphorus byproduct, so what we really care about is what happened to the ketone. Often you don't see the reaction this way, but rather you see the ketone as the starting material. So let's rewrite this in a form that you're going to be used to seeing it. It was only written this way so that we could step through the mechanism in a linear fashion and show you how the ylid was prepared. Oftentimes you can just use the ylid directly. I'll show you how to do that. We would use just this as the reagent. Okay, so again, you would use either some kind of a carbon ion with the triphenylphosphine attached and some kind of R group. And it's possible this would look different. You could have 2 R groups here, for example. Okay, or you might specify what the R group is. They should. All right, another way you might see that is in the double bond format. So in either case, you should know that this carbon group is what's going to replace the oxygen, and you're going to end up with an alkene. So here's how you do that. These R groups continue to remain there. To me, it sort of reminds me of like a reverse oxidative cleavage. Like instead of cleaving an alkene and putting the oxygen there, we're doing the opposite. We're taking the oxygen away. So, and where does oxygen end up? It ends up with the triphenylphosphine. Okay, so we're going to use this group right here. So I have a carbon, a hydrogen, and an R group. And we've said it was R prime. So just keep that going. Okay, ultimately, then we've got this is being replaced with this. And there it ends up. Okay? This is a really weird reaction to get used to. So what you want to pay attention to is that you're going from a carbonyl group, like a ketone or aldehyde, and you're going to an alkene. So if it helps you to write out the words, please write out the words. Okay, it's going to take a while before you can really see when to use this reaction. So don't worry, plenty of practice problems for you to work on that. All right? Okay. And here they are. These are actually problems from the Stromanis text, which I find very useful. There's also problems in your textbook Klein that I also find useful. I would say just do as much practice as you can. You know, use one practice and then use another one to test yourself. Okay? So let's say you do this practice just to learn it. Maybe you're looking at the answer key a lot. Maybe you're going back and forth trying to figure things out. Then use the Klein problems as a way of testing your knowledge then, okay? But, you know, the more practice you can do, obviously, the better. You'll find things that you don't quite understand as well, and then you'll be able to learn them through the problems. All right, so I'm going to do a video, hopefully, on walking through these practice problems, but in the meantime, please try them and check your answers as well and see where you go wrong, and make sure you ask me questions if you get stuck. All right, good luck.